Okay, next example. Here we have the same pyramid problem that you saw at the beginning of the video, and this is the Pyramid Arena in Memphis. It has a square base of side approximately 600 feet. So one side from here to here at the base is 600 feet, okay, or from here to here. And a height of approximately 320 feet. So if we were to measure the height from here, from the very top, put a line perpendicular to the ground, you would get 320 feet. And we want to find the volume of a pyramid with these measurements. Alright, so this one they didn't give us a formula, so we're going to have to come up with the formula ourselves. It's a little bit trickier. But if you think about what your cross sections look like, it says that you have a square base, right? So you know your cross sections are squares. So we're cutting this pyramid like this, and these cross sections that we're going to end up having here are going to be squares, okay? But they're changing. As we're closer to the bottom, we're at 600 feet, and as we go up to the top, we're going to come up to a side with a square of 0 feet. So we want, or we need to find the following. We need a formula for the size of a cross-section. Right, that's what I want. I want the area of my cross-section. That's what I want in each of these. So we need the area of cross-section given the height. So I want to put in height and I want to get out the area. So I want the area of the cross-section in terms of the height that we're at. So if we put in this height right here, we want to know what's the area of that square cross-section. Okay? Our cross-sections, like we said, are squares. They decrease in area as the height increases. So let's figure out how to come up with a formula for this. Well, when h is equal to 0, we know that the cross-section is a square with side 600 feet, right? Cross-section has a side equal to 600 feet. And when our height is all the way up there at 320 feet, then our cross-section has a side of 0 feet, right? Once we get up to the top, we don't have any width to our square anymore. So let's let f of h represent the side length of a cross-section. Okay, I'm going to let that represent the side length of my cross-section. So you can see that this is a formula, right? The side of the cross-section down here, it's this big. Here it's this big. Here it's this big. Here it's this big, right? So this is a constantly decreasing. In fact, it's actually a linear function because our sides of our pyramid are not curved, so it has the same exact rate of change as we go up. Okay, so the length, if you think of f of h as the side length of a cross-section, that's what the function is. The function is describing the outputs of the function. We're putting in height, we're getting out the side length of the pyramid. Okay, so that's what our f function describes. It's the side length of the cross-section for a given height. We input 0, we get out 600. We input 320, we get out 0. And we know it's linear because it's constantly changing. Our rate of change is constant. It's not getting, we don't have a pyramid that looks like this where it's changing at different rates. Our sides are changing at a constant rate. So basically what we have here then is we know we input 0, we get out 600. And if we input 320, we get out 0. And we know this is a linear function, so we have 2 points. We know it's a line, so we can figure out what that function is. So our slope then would be the change in y, which would be 600 minus 0, divided by the change in x, which is 0 minus 320, right? So that slope comes out to negative 15 over 8, and that makes sense. It's a negative slope because it's a decreasing function. We have a large side length at first, smaller, 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 up to 0. So our function is going to come out to be negative 15 over 8 h plus 600. Okay, so remember that this represents the side length of the pyramid, or the side length of a cross section. Alright, so we're almost done here. We don't just want the side length though, we want the area of a cross section. And since we know these are squares, we can say, well then the area in terms of height that we wanted, remember that's what we needed back up here, the area in terms of height is going to be the length of a side squared, so it's f of h squared, right? Or that would end up being negative 15 over 8 h plus 600 quantity squared. So the area in terms of height of a cross section of this pyramid is negative 15 over 8h plus 600 quantity squared. Okay? So we got to that from finding the length of the side and then squaring the length of the side. Okay, but what are we trying to find? Well, we're trying to find the volume. So now we need to integrate those area pieces from 0 up to 320. So this is what we'll have. The volume is going to be the integral from 0 to 320, right? And this is going to be in terms of the height. And we have our function already in terms of the height, and our function for the area. Let me just put area in terms of height right here. That's what I need. Okay? So I'm integrating the area. You're always integrating your area formula in here. I'm pointing at the screen with my finger and realizing you can't see me doing that. You always want to integrate, what you put in your integral is that area formula, the area of the slice. Okay? Area, and you integrate it from wherever it's going to wherever it's going. So that's going to end up being 0 to 320. Our area formula was negative 15 over 8h plus 600 quantity squared dh. That's my area formula. Okay, and then we can just integrate that. If we were asked to do it by hand, we could call this part inside here u. If not, you can just do it on your calculator using your fn int formula. It would be fn int of your function, comma h or x or whatever you want to use, comma 0, comma 320. Okay, if we were asked to integrate this by hand, though, we could do that. And we would just let u be this part inside here. Okay, so u would be negative 15 over 8h plus 600, which means that du would be negative 15 over 8 dh. It's just the derivative of this u function times dh. Alright, and so then I'm going to need to identify that du in my function, so I'm going to have to multiply inside and outside of my integral by negative 15 over 8, or multiply and divide. Alright, so I want negative 15 over 8 dh, because I want to have du in here. So I'm going to have to multiply on the outside as well by negative 8 over 15, because those would cancel, and then I haven't changed my integral any, I've kept it all balanced. Okay, so that would give me negative 8/15, and I'm going to have to change my limits on my integral as well, and we'll talk about that in just a minute. And then I have this part in here, negative 15 over 8h plus 600 times negative 15 over 8 dh, and that's my du. So this is du, and this is u, so I'm going to have u squared du. Now my limits, let's think about the limits. If the height is 0, what is negative 15 over 8h plus 600? What did that represent? Let's go back here. What was that? That was my f of h function, right? Which represented the side length of my cross section. So what is the side length when our h value and our height value is 0? We're going from 0 to 320. We already know those values, right? So what is the side length? U is the same thing here as our f of h function, which is the side length. So what's the side length when our height is 0? The side length is 600. And what's the side length when our height is 320? It is 0. So this becomes integral from 600 to 0 of u squared du times negative 8/15. Okay. 600 to 0 of u squared du. Alright, and now we could evaluate that. This would give me u cubed over 3 from 600 to 0. And we have our negative 8/15 times that. Okay. So then that's going to give me negative 8/15 times, remember you plug your 0 in first, so 0 over 3 minus 600 cubed over 3. Right, and the negatives are going to cancel, negative times a negative, so we just end up with 8/15 times 600 cubed over 3. And that should simplify to 38,400,000 cubic units is the volume of our pyramid. Okay, so that one was a bit of work. Look back at what we did real quick. We needed a formula for the cross-section given the height. We said we had 2 points basically where we could figure out what a function for the cross-section is, or for the area of the cross-section is. Given 0, our output, our side length was 600. So for the height of 0, our side length was 600. For a height of 320, our side length was 0. And we found a function that represented the side length right here. And then if we squared that, that gave us the area of our representative slice. And then we integrated that representative slice from 0 to 320. And like I said, if you can use your calculator, you can stop right here and just put that in your calculator. Okay, one more example. Volume of known cross-sections, example 3. Suppose a dome has circular cross-sections with outline y equals plus or minus the square root of 45 over 2 times 90 minus x. That's this curve here, this blue curve, okay? For 0 is less than x is less than or equal to 90, so from 0 up to 90. And in units of feet, this gives dimensions similar to the Capitol Dome in figure 513b right here. So similar dimensions to the Capitol Dome. A graph of this sideways parabola is shown right here, and we're going to find the volume of the dome. Alright, so that's our problem. It has circular cross-sections, so we know we're going to have circular cross-sections like this. And we're going to be integrating that from 0 up to 90. Alright, so I'm going to draw it this way, just to kind of give you a little bit better idea. They said it was looking like the Capitol Dome, so it would be like this. And your circular cross-sections, put those in here. So we know all of these are the same, they're all circles, right? But they're not all the exact same size or the same shape, but they're not the exact same size. We're going to have to find a formula for that shape. Okay, and that's what it would look like if you put it up and down like that, but it's really turned over on its side this way. Okay, so that we have a formula in terms of x. Okay, so we're going to be integrating, and we're going to be integrating from 0 to 90, it looks like, right? We're summing all of these little tiny, tiny slices. If I can make this look like it has some volume here. Okay, so I'm finding the volume of that tiny slice. I'm integrating from 0 to 90, summing all of those up from here to here. I need a formula in here, and this is going to be in terms of x, right, dx. And I need a formula for the area of my slice. That's what I'm doing. So what's the area going to look like? Well, let's look back here. The area is, you know, it's going to be pi r squared, because it's the area of a circle. And that means we need to figure out a formula for the radius, right? Because that's constantly changing. The radius is this, and then it's this, and then it's this, and so on. So the radius is whatever the function value is, right? It's the distance from here to here, which is just whatever the function value is. So it's the y value. That's what the radius is. And we just want that in terms of x, so we're going to use this formula right here. This curve, this top curve, is the positive square root of 45 over 2 times 90 minus x. Okay, so that describes the distance from here to here, that function value. So area in terms of x then, well, first let's do radius in terms of x. The radius is just the function value, the square root of 45 over 2 times 90 minus x. And the area then is going to be pi times the radius squared. So pi times the radius, 45 over 2, 90 minus x, quantity squared. And since I'm squaring a square root, I can just simplify that to pi times 45 over 2 times 90 minus x. Alright, and then when I find the entire volume, I'm going to sum all of those slices from 0 to 90, so I'm going to have the integral from 0 to 90 of my area function, right? And that's going to become integral from 0 to 90 of pi times 45 over 2 times 90 minus x dx. Alright, and if you don't need to do this by hand, you can just go ahead and stop there, put that into your calculator, and simplify it. I'll go ahead and work it out by hand for you. I can factor the pi out of my integral. I have integral from 0 to 90 of 45 over 2 times 90 would simplify to 2025. And then I'm going to have minus 45 over 2x, right, distributing that 45 over 2 dx. Okay, so 45 over 2 times 90 gave me 2025 minus 45 over 2x. I factored out the pi. I don't have to do any u substitution here. I don't have an inside function. I just have this nice term 2025 and this other nice term 45 over 2x. I can integrate both of those. So I'm going to end up with pi times 2025x minus 45 over 2 times x squared over 2. And that's all from 0 to 90. So I get pi times 2025x minus 45x squared over 4 from 0 to 90. And when I plug in 0, everything's going to go away, right? Because I'm going to have 0 minus 0. So I really just have to plug in 90 here. So I get pi times 2025 times 90 minus 45 times 90 squared over 4. And like I said, I would do minus and I would plug in 0, but that's just going to come out to 0 minus 0. Okay? So that should all end up being 91,125 times pi as the volume of the dome. Alright, so that's it. That's all I have for volumes of known cross sections. Let's go back here real quick and just review for a minute. With volumes of known cross sections, all you've got to do is find the area of your representative cross section. And once you find the area of that representative cross section, you just sum it from here to here. So it's generally finding this area formula that's the hardest part. Once you find that area formula that works whether you are down here or up here, then you can just integrate it and sum from wherever to wherever. Alright, that's it for volumes of known cross sections. I'll see you in the next lesson.